Hello everyone. In this video, we are going to write a Verilog file that runs the fast Fourier transform algorithm on an FPGA. We will do this by taking the algorithm that we discussed in the last video and converting it step by step into synthesizable Verilog. This lesson will teach you two important things. First, how to take an algorithm that has been expressed in code and translate it into Verilog. This is a skill that comes up constantly in digital design, and the fast Fourier transform gives us a great example to practice on. Second, this lesson will give you real exposure to the kind of intense, detailed Verilog work that goes into building a custom IP block. In practice, you usually don't write everything from scratch. You use pre-built IP, but the engineers who create those IP blocks, like the one we'll use in the next video, had to write thousands of lines of Verilog code to make them. So by going through this process ourselves, you'll get an appreciation for what's actually happening under the hood. Before we begin, let's quickly review the complete FFT flow from the last video. To compute the FFT, there are two steps. First, we take the input vector and pass it into the getFFT input function on the left. Then, we take the output of that function and pass it into the FFT function on the right. The output of the FFT function is our final result. In this video, our goal is to take the FFT function on the right and turn it into Verilog. The code on this slide makes the entire process more clear. We start with our vector of samples S. We pass S into the getFFT input function to get the reordered vector, and then we pass that reordered vector into the FFT function. In this video, we will only be writing RTL to implement the FFT function, since that is where 95% of the effort is. The reordering function is much simpler and will be left as an optional exercise. Before we start writing Verilog, it helps to first rewrite the Python so that it more closely matches what the hardware will actually do. On the left is the original FFT function, and on the right, we have rewritten it so that each step in the loop body is its own distinct operation. So now we can take that rewritten code and map it directly onto hardware. Each piece of code gets its own dedicated module. The loop gets its own module, the getW function call gets its own module, the getAB function call gets its own module, and so on. Note that the two lines accessing memory must use the same shared memory module. To prevent this video from getting too bogged down in the Verilog details, I will only discuss the functional behavior of each module at a high level before showing the demonstration. So let's start with the counter module. The counter takes in three main inputs: start, max I, and max j. Each time the start is asserted, the counter updates its I and j outputs to the next pair in the sequence. You can see the pattern in the table. J counts up from 0 to max j, and once it rolls over, I increments by 1. This repeats until we've hit max I and max j, so by pulsing this module over and over, we emulate the exact nested loop that the Python code runs through. The waveform at the bottom shows this behavior in simulation. The getW module is a mathematical block that takes in two inputs, I and j. From those two inputs, it calculates W real and W imaginary using the two formulas shown below. To implement those two equations in hardware, we needed dedicated arithmetic modules for each math operation. The block diagram here shows the full chain. You can see I and j come in on the left, and each subblock computes one piece of the formula until we get the final angle, which gets passed into the sine and cosine calculator to produce W real and W imaginary. For the sake of time, I won't walk through the Verilog for each of these submodules, but they are all built using the same general methodology that we covered in the fixed point section of the course. Also note that if you purchased the course book, you will get access to the project files, giving you the chance to look at the specific details on your own time. Purchasing the book also gives you access to the private Discord server, where you can collaborate with others and ask questions directly to me. The getAB module is another purely arithmetic block that calculates two numbers, A and B for a given I and j using the formulas shown here. Since all of the operations involved are just shifts, additions, and modular arithmetic, this one is simple enough to be handled by a single sequential module. The butterfly module is also just an arithmetic block. It takes in 6 inputs and produces 4 outputs using the equations shown here. These are the same butterfly equations that we covered in the last video, just written out in terms of their real and imaginary components. In hardware, this is implemented by chaining together multiplier, adder, and subtractor blocks. The controller's job is simply to do the following: pulse the counter module, pulse the get W module, and then wait for the done pulse, pulse the get AB module, and then wait for the done pulse, pulse the read ports of the RAM, pulse the butterfly module, and then wait for the done pulse, and then pulse the write ports of the RAM. The controller will repeat this indefinitely until the entire loop has finished. To verify this module, I used an automated test setup. There's a Python program, the RTL source file, and a test bench. The Python program drives the Vivado simulator automatically. It feeds in a test case, runs the simulation, then compares the output against a golden reference computed in the Python. If they match, it logs a pass. If not, it logs a fail. It then repeats this for many different test cases in a row, so the entire verification process is fully automated. This is much faster than manually running each test in the Vivado IDE. If you want to run this test yourself, you just need to point the Python script at your Vivado installation, the source file, the test bench, and the cosine and sine ROM files. So to wrap up, the Verilog that we built in this video implements the FFT function and only the FFT function. It assumes that the data has already been reordered and loaded into RAM. So to make this a fully standalone piece of IP, you would need to build additional circuitry to handle that reordering step, or even better, an address generator that takes care of it for you. That part is left as an exercise. Also, the entire project uses S16.16 fixed point format, meaning every number is represented with 16 bits of integer and 16 bits of fraction. Also note that in the project files for this lesson, there is a folder containing everything you need to verify a single test case. Here is a quick demonstration of that in action. We first run the Python program, which initializes the test bench with the correct values and generates a golden reference. Then we run the test bench and check the output in the terminal. If this passes, we know that the hardware produced the correct result. That's all for now, and I'll see you next time.